Yes friends, welcome once again to the class, and we will discuss today chromatic aberration in a lens. Okay, chromatic aberration of a lens we will discuss, and in this chromatic aberration of a lens we have something called as refractive index, which is different for different colors. Okay, so that's the thing. What is exactly chromatic aberration we will learn over here. So refractive index is your function of wavelength or color, as written over here. Refractive index n is a function of wavelength or color. In general life we say that whenever refraction takes place via a lens, then a point image is formed. We call it like that, but in reality a point image is not formed. Okay, because for different color of the electromagnetic spectrum, Vibgyor, which you might have learnt in your lower classes. So for violet, the refractive index is different. For red color, the refractive index is different. For indigo color, the refractive index is different. For every color, the refractive index will be basically different. Okay. So, so the situation is that the refractive index is different for different color. So by Cauchy's empirical formula, the refractive index and wavelength of a color, the refractive index and wavelength of a color are related by this particular formula according to Cauchy's empirical relation. Okay, you need not go into this derivation of this Cauchy empirical relation, but you can understand from this Cauchy's empirical relation that the refractive index and the wavelength are related something like this. Okay, now n is minimum for red color, and your n is basically minimum for red color, minimum for red color, and n is maximum for violet color. Why? Why n is minimum for red color and n is maximum for violet color? N is minimum for red color because the value of lambda, the value of wavelength, that is lambda, the value of wavelength, that is lambda, is maximum for, because lambda is maximum for red, because lambda is maximum for red, that's why n will be minimum for red according to this formula. And as lambda is minimum for violet color, so when we put the minimum value of lambda in this, because lambda is there in the denominator, right? So when lambda will be minimum, your n will be maximum. Okay, so this is the reason for this. Now focal length of a lens, focal length, focal length of a lens, focal length of a lens, f is equal to your f of n, function of n. F is your function of n. As why your focal length f is a function of n? As 1 over f is equal to n minus 1. This formula we have already derived in the previous lectures. Okay, so 1 upon r1 minus 1 over r2. Okay, so according to this formula, f is also your function of n. Okay, now so we can say from here that as your n is a function of, okay, so we can say from here, as n is a function of lambda by Cauchy's empirical relation, that implies what? That implies that your f will also be a function of, that implies f is also, focal length f is also a function of lambda, that is wavelength, or we can say color, because color depends on wavelength. That's why f is also a function of your lambda, that is your color. Okay. Now the electromagnetic, the visible spectrum. The visible spectrum consists of 7 colors, which are violet, indigo, blue, green, yellow, orange and red. Okay, violet, indigo, blue, green, yellow, orange and red. Okay, this is your short form which you have learnt in your lower classes. So you only tell me that clearly the lambda value as already discussed over here, lambda is minimum for violet color and lambda is maximum for red color. Okay, so lambda for red is greater than lambda for orange, it is greater than lambda for yellow, it is greater than lambda for green, it is greater than lambda for blue, it is greater than lambda for indigo, it is greater than lambda for violet. Right? Now you know this very well, that by Cauchy's empirical formula, by this particular formula, whatever order lambda follows, n will follow exactly opposite order, because n and lambda are inversely proportional, not exactly inversely proportional but almost. Okay, means we can say as lambda increases n decreases, and as lambda decreases n increases, we can say. So from here what do you get? That implies by Cauchy's empirical relation, refractive index of R, that is red, will be smaller than refractive index of orange, that will be smaller than refractive index of yellow. Okay, that will be smaller than refractive index of green, that will be smaller than refractive index of blue, that will be smaller than refractive index of indigo, that will be smaller than refractive index of violet. Right? So this is the order which refractive index follows. Now from this particular relation, the focal length will follow the opposite order as n, as f is in the denominator and n is in the numerator. So focal length will follow exactly an opposite order as compared to refractive index n. So focal length will follow an exactly opposite order. So similarly, focal length will follow the order. Which order will the focal length follow? This same order. Okay, same order for focal length. Okay, so let's write in the next page. The order for focal length is, thus the order for focal length is, the order for focal length will be f of r will be greater than f of, not f of frequency for red will be greater than frequency of orange, that will be greater than frequency of yellow, that will be greater than frequency of green, right? That will be greater than frequency for blue, okay? That will be greater than frequency for indigo, that will be greater than frequency for violet, okay? So this is the order for focal length. Now write one note over here, you will understand this as the class proceeds. Image of a point, okay, image of a point object image of a point object found by a lens, image of a point object found by a lens is not a point image but a linear spectrum. Let us understand this with the help of a okay. Let us understand this with the help of a figure. Suppose I have a lens over here. Suppose I have a lens over here. Okay, let us draw it properly. Okay, let us have a lens over here. And suppose there are two rays coming from the infinity. Okay, suppose there are two rays coming from the infinity. Okay, these are parallel rays which are coming from infinity, and suppose this is your axis of the lens, optical axis of the lens. So this will be your refraction. In general, we call that this infinity object as parallel rays are coming from the object at infinity, so it will be focused at the focal length, we call like that. But in reality, I have already told you that the refractive index for violet will be maximum. From here you can see that from here, this expression, you can see that the refractive index for violet is maximum and the refractive index for red is minimum. So violet will undergo maximum deviation. Deviation. Okay, so violet will undergo maximum deviation. So according to this figure, this violet, this is the point at which violet image is found. This is the point at which violet image is found. This is your violet, and this is the point where red image is found, where the red light is focused. As the rays are coming from infinity, so they are focused at the focal length. Okay, so this is what, this is your focal length. This is your focal length for the red color, and I have already told you that the focal length for the red color is maximum and focal length for violet color is minimum. Okay, so this is the point at which violet color is focused. This is the point at which violet color is focused. So this is your FV, means focal length for violet color, and this is the focal length for red color. Okay, and this I can write as this I can write as the violet focus point, and the focal length, this is your focus point for red color. So there is a blurred image. As a result, the image will be blurred because the image is dispersed. The image is dispersed in this complete area. Image is dispersed in this complete area. So instead of a point image being formed, a line is being formed over here. A line has been formed. A line has been formed over here. Okay, a line has been formed instead of a point image. Okay, although the object was at infinity, but instead of getting a point image, we will get a line instead. Okay, we will get a line instead. So you will understand this more and more clearly as the class proceeds. Image of a point object formed by a lens is not a point image but a linear spectrum. This is what is meant by this. Okay, but a linear spectrum. Okay, let's write one definition over here now. But a linear spectrum. Variation of the image distance, right over here. Variation of the image distance for a given object distance. Variation of the image distance for a given object distance with refractive index or color is known as longitudinal or axial chromatic aberration. So variation of image distance for a given object distance with refractive index or color. Okay, so with refractive index you can clearly see this, that the refractive index are different. Refractive indices are different for different colors. Refractive indices are different for different colors. Wavelength are different for different colors. Because wavelength is different for different colors, refractive indices are different for different colors. As a result, focal lengths are different for different colors. Okay, so because of colors, there is a variation in the focal length also. Okay, and the refractive index also. So variation of the image distance for a given object distance, there will be a certain object distance u and image distance will be v, and the image distance will be different for different color clearly, because the refractive index is different for different color clearly. Okay, so with refractive index or color, as the color is different, that's why refractive index is different. Because color is different, that's why wavelength is different, and as wavelength is different because color is different, that's why refractive index is different, and as refractive index is different, that's why focal length is different. Okay, is known as longitudinal or axial chromatic aberration. Now why we have called it longitudinal or axial chromatic aberration? Why we have called it longitudinal or axial chromatic aberration? This is because it is along the axis. Okay, it is along the axis. A line is being formed along the axis. Okay, that's why axial chromatic aberration. Okay, or longitudinal, because this is basically your axis is also called as longitude. Okay, axis is also called as longitude. So that's why means it is similar to longitude. Okay, its meaning is similar to longitude. Axial meaning means similar to longitude. So that's why it is called as longitudinal or axial chromatic aberration. Okay, now let us write over here. Let us write your axial chromatic aberration is given by what? Your linear chromatic aberration, longitudinal chromatic aberration, LCA, is equal to your nu r now this is longitudinal chromatic aberration. The value of longitudinal chromatic aberration will be given by let me just see it, friends. Just a second, friends. Okay, just a second. Yes. So linear chromatic aberration will be given by your VR minus VV. Okay, in general. This is what? Longitudinal chromatic. LCA means longitudinal chromatic aberration. Okay, VR minus VV in general, where VR is what? Where VR is equal to object distance for red color. Okay, and VV is equal to your object distance, not object distance, image distance, sorry. Okay, not object distance, image distance. Image distance for red color, and this is your image distance for violet color. Okay, never get confused. Okay, your red color has a greater image distance because its refractive index is least, so its image distance is greatest because least deviation takes place. Okay, so VR is greater than VV, so that's why VR has been written first, because object distance for red color is always greater than the image distance for violet color. Okay, image distance for red color is always greater than image distance for violet color. That's why VR has been written first, because refractive index is minimum for red color. That's why image distance is maximum for red color. Okay, as the refractive index is minimum for red color, that's why image distance is maximum for red color. Okay, so hopefully you got this. Since the focal length depends on the color, okay, so magnification will also be different, right? Since the focal length is dependent on color, so magnification will also be different. Okay, so let's write over here since the focal length depends on the color that is wavelength of light. The images of different colors are magnified the images of different colors are magnified to different extents. Images of different colors are magnified to different extents. This is quite obvious, right? Focal length will be different for violet and red and different colors in the visible spectrum. So obviously as the focal length will be different, so obviously this will also be different, magnification will also be different. So images of different colors are magnified to different extents. This defect is called the lateral chromatic this effect is called the lateral chromatic aberration. Okay, so for example your red color will be magnified larger. Okay, for example, let us write over here. For example, for the same object distance, red color image will be magnified to a larger extent because its focal length is maximum. Okay, whereas violet colors image will be magnified to a lesser extent because its focal length is minimum. Okay, minimum. So for the same object distance, if the object emits, two objects are placed at the same distance, one of the object emits red color and another object emits violet color. then the object emitting red color will be magnified larger. Its magnification will be larger. The image formed will be larger as compared to that formed by the violet color. Okay, violet color will form a smaller image. Okay, a smaller image. Violet color will form a smaller image. So this is what is meant by lateral chromatic aberration. Why we have called it lateral? Because now as we are talking about magnification, so we are talking about this area, this particular area. Okay, like this, we are talking perpendicular to the axis. Magnification is always perpendicular to the axis, right? So as we are talking about perpendicular to the axis, so that's why we are calling it to be lateral. Okay, and when we were talking along the axis, we were calling it longitude. Okay, so this is the thing. Now let's write over here the combined effect of the combined effect of both of these aberrations causes a blurring of the image. Okay, blurring of the image will take place because instead of getting focused at a single point, the image will be focused over a area. Okay, instead of being focused at a single point, the image will be focused over a area. So combined effect of both these aberrations causes a blurring of image. Okay, this defect in this defect in color and definition means how sharp the image is formed. Definition means how sharply the image is formed. This defect in color and definition is known as chromatic aberration in general. Okay. This is known as chromatic aberration. Okay. So let's draw one figure over here. Let's draw one figure. This is the optical axis of the lens. These two are incident rays. Okay. This is the point at which red color is getting focused. This is the point at which violet color is getting focused. Okay, so this is for violet color, this is for violet color, and this is for red color. Okay, and your arrows are like this. Okay, Now this is what? This is your pole of the lens. So you will measure the distance from here till here. This is what? This is your FR. And similarly, when you measure the distance from here till here, this is what? This is your FP. Okay. Okay, from here till here. And this is from here till okay. So in this manner you can understand the situation. Now object distance for red is equal to your focal length for red, because as u equal to minus infinity, right? Minus infinity, because the object is placed at infinity, and whenever you measure the distance from here over here, it is taken as negative, and whenever you measure the distance from here over here, it is taken as positive. Okay, you know this very well, because the distance measured opposite to the direction of wave propagation, light propagation, the distance when it is measured in opposite direction of light propagation, it is taken negative, and when the distance is measured along the direction of wave propagation, that is taken as positive. Okay, so VR is equal to your FR, and similarly your VV is equal to your FV over here, again as u is equal to your minus infinity. Okay, so this is in this way you can understand the chromatic aberration, okay, of a lens. So we will discuss the expression for axial or longitudinal chromatic aberration in the next class. Okay, so thank you very much. Thanks for watching the class.